In this subtopic, block diagram description. Now we will see what is block diagram, what are the different components of a block diagram, why it is required. Okay. Why block diagram is required? See, it can be used to simply describe the composition and the interconnection of a system. Okay. For example, if we take a DC motor control system, and if we want to represent it in a form of block diagram, then I am having some input voltage. That input voltage is going to some amplifier. This is my amplifier. Output of amplifier is going to DC motor. Output of DC motor is going to some load. Okay. And finally, output is speed. So, changing the input voltage will lead to change in speed. In between this, there is some disturbance also present here. So this is a block diagram description of a DC motor control system. So it just shows the interconnection and the composition of overall control system. Okay. Now similarly, block diagrams can be made for any of the control systems. Okay. So in block diagram, there are points like this, which are called the summing points. They can also be a multiplier. Okay. There can be somewhere minus also may be there. Okay. So likewise, the output of this, and the output of this. Suppose this is RT and this is some HT, then in this case it will be RT plus HT. In this case it will be RT multiplied by HT. In this case this is RT, this is HT, and this is suppose XT. Then it is RT plus HT minus XT. Okay. So these are one of the composition for any control system. Or when we represent a control system by making use of block diagram, I can write it like this. Now, a very basic block diagram of feedback control system is drawn like this. This is my summing point. Input here is RT, or Laplace transform I can write it as RS. This is my error signal, which is going to another block which is having transfer function GS. Output is coming as CS, or it can be CT. Feedback of this is going as a output summing point. This is, you can write here BT or PS. This is a basic block diagram of a feedback control system. Particularly, this is a type of negative feedback. Now, various components of this RT oblique RF is called reference input. Okay. CT oblique CS is called output. This one is controlled variable because it is controlled. For controlling this only, we have made the full function, we have made the full block diagram, we have made a control system. Okay, the output is controlled one. BT oblique BS, this is a feedback signal. ET oblique ES, it is a error signal. This error signal is equal to RT minus PT. Okay. GS into HS is open loop transfer function. GS is equal to forward path transfer function. HS is feedback transfer function. Okay. Overall transfer function is equal to CS by RS. So these are the various components of the given basic block for a basic block diagram of a feedback control system. Okay, it is same for either it is a negative feedback or it is a positive feedback. Okay, but the transfer function, overall transfer function, that will change. We will see the derivation of that. By looking at the block diagram, I can write my CS is equal to GS into ES. Okay. BS, which is a feedback signal, is given by CS into HS. Error signal ES is given by RS minus BS. So I can write this as RS minus CS into HS. Okay. Substituting, let this be equation number 1, this be equation number 2, this be equation number 3. Substituting 3 in 1, I'll get CS equal to GS multiplied by RS minus CS HS. Okay, this will be GS into RS minus GS into CS into HS equal to CS. Now, on manipulating this, I will have CS upon RS is equal to GS upon 1 plus GS HS. So this is my overall transfer function for the basic control system negative feedback block. Okay. If it is positive feedback, I will directly write the expression GS upon 1 minus GS HS. For positive feedback. This is for negative feedback. Okay. So this is the block derivation for finding the negative feedback. But we should not worry about the derivation. We should know how we have achieved this and we should remember this or this. Because most of the time in exam we may be directly using this or this rather than going into the derivation. Okay. Now the second subtopic is introduction of block diagram. Okay. So this topic, reduction of block diagram, is useful while while finding the overall transfer function. Okay, for a complicated combination of block diagrams. Okay. See, the first one in this is, suppose if two blocks are in cascade. Let this be G1, let this be G2, this is X, and this is Y. The overall combination of this will be G1 multiplied by G2, input X, output Y. Okay, simple one. Now, second is moving a summing point after block. Okay, moving a summing point after a block, the basic principle followed here is the output should remain same. See, suppose I have this summing point plus this is my x1, this is x2, and here one block which is given by G. Here it is coming x1 plus minus x2. Output here is coming G of x1 plus minus x2. Okay. Now if I want to move by this summing point to here, then what should I do? See, the thing is that output should remain same. Okay. For output to be same, I need to multiply here by G plus I need to multiply here also by G plus minus. This is my x1, this is my x2. So output of this is x1G, output of this is x2G, output of this is x1G plus minus x2G, which is equal to G times of x1 plus minus x2. Okay, so the principle for moving a summing point after the block or before the block, or moving a takeoff point away from the block or ahead of the block or before the block, is simple as that. Output should remain same. Okay, the overall which is coming from the point, that will remain same. Now we'll see a third one, moving a summing point ahead of the block. That means we need to move this summing point before the block. Initially it is given, in this case it is before the block, now it will be ahead of the block. Third case is this. Output coming here is gx1 plus minus x2. Okay, from this I want to move my this point ahead of this. Ahead of a block. While doing this, if I want to move my this summing point ahead of this block, then I should be careful so that my output should be this. So when this will be the output, suppose if I move it here, G, input coming here is x1 plus, it should be multiplied by 1 by g. Put coming here is x2. So now at this point I will have x1 plus minus x2 by g, and the output of this is gx1 plus minus x2. Okay, so we need to multiply by 1 by g in the x2 path. Okay, the fourth one is for the takeoff point. This one is only for the summing point. Now there is another point which is called takeoff point. Moving a takeoff point after a block. I am having takeoff point from here. This is my x1, my x1. Suppose if I want to move this takeoff point to this point, what should I do? Again, that point, the value of this point, the output at this point should remain same. I can write g, this is x1, one by g, x1. Okay, because the output at this point is x1g. So x1g when it will pass through this particular when it will pass through this particular block, it will become only x1 because 1 by g and g will get cancelled. So this is the procedure for moving a takeoff point after a block. Now the fifth one will be moving a takeoff point ahead of a block. Moving a takeoff point ahead of a block. In this case, already takeoff point is after the block. My x1, this is g, this is x1g, output coming here is x1g. If I want to move my takeoff point my x1, this is g, this is again x1g, this is also g, this will be x1g. Okay, it will be like this. So it will lead to a multiplication by g. If we want to eliminate feedback loop, then this is my r, this is my c. I can write by c by r is nothing but g upon 1 minus plus gh. Okay, so this is in this way we can eliminate the feedback loop and can directly write one block instead of this. Okay, so this way this is